So here we have a transformation L that maps elements from W to V, where V is equal to polynomials, set of polynomials with real coefficients, which is also a vector space, and W is equal to the set of all functions, or I should say all polynomials with real coefficients f of x in V, such that f of 0 is equal to 0. Okay, so W is a subset of V. So what we have here is that L takes an f of x, a polynomial, in W, and maps it to an element in V. So L of f of x is going to be some polynomial in V, and that's going to equal to f prime of x. So essentially, L, this transformation, takes f and maps it to its derivative. Okay, and if f of x is a polynomial, then its derivative is also a polynomial. Okay, it's just going to be 1 degree less. Okay, so that's what we have right over here. So now, the first thing is, let's check if W is a subspace of V. We know that W is a subset, but is W a subspace? So all subspaces are subsets, but not all subsets are subspaces. In order for it to be a subspace, it must be closed under addition and scalar multiplication. So what that means is, if I take f of x and g of x in W, is it true that f of x plus g of x is also in W? Okay, so that's the first thing we need to check, closure under addition. So let's say we have f of x and we have g of x, they're both in W. What does that mean? It means that f of 0 is equal to 0, which is also g of 0, right? Because that's just a condition, right? If you're a polynomial in W, that just means the polynomial evaluated at x equals 0 is 0. Okay, so we have f of 0 is equal to g of 0, which equals to 0, because they are both in W. That's just a condition for it to be in W. Okay, we have arbitrary polynomials f of x and g of x that are in W, so they must respect this condition. So now, is it true that f of x plus g of x is also in W? Well, let's see. So f of x plus g of x, we know f of x plus g of x is a polynomial, but in order for it to be in W, its value evaluated at x equals 0 must give me 0. So if I call this h of x, okay, is it the case that h of x is in W? Well, let's see. This implies that if f of x plus g of x is equal to h of x, this implies that h of 0, okay, if h of 0 is equal to 0, then all of this is in W. Okay, so h of 0 is equal to f of 0 plus g of 0. Okay, so you're essentially just subbing in 0 for x's. Okay, what is f of 0? F of 0 is 0. What's g of 0? G of 0 is 0 from here. And 0 plus 0 is 0. So we get that h of x, which equals to f of x plus g of x. All of this, f of x plus g of x, is in W. So it is closed under, so W is closed under addition, which is nice. So now we shall check for scalar multiplication. So again, f of x isn't W, which implies that f of 0, oops, I should move this down a little bit, is equal to 0. So now, if I have it that C times f of x, okay, C times f of x is equal to h of x, where C is just some arbitrary real number. This implies that h of 0 is going to be C times f of 0, which equals to C times 0. What's C times 0? A constant times 0 is 0. A number, any number times 0 is 0. Okay, so this implies that h of x, which equals to C times f of x, is in W, which implies that W is closed. Under scalar multiplication. So that is good. So therefore, W is a subspace of V. Okay, so that's what we have over here. Coolios. So now the second part is we need to show that L is a linear transformation. At the beginning I said it's a transformation. Okay, we need to show that it's a linear transformation. What does it mean to be a linear transformation? This means that it must respect addition and scalar multiplication. Okay, so what that means is it a case that given, let's say, f of x and g of x in W, is it true that L of f of x plus g of x, is this the same thing as L of f of x plus L of g of x? Okay, so let's just do this. L of f of x plus g of x, okay? What that means is I'm taking the derivative, right? So L of a polynomial is its derivative, okay? So L of f of x plus g of x is going to be equal to the derivative. Well, if I call this whole thing h of x, right, then h prime of x, or the derivative of h, is just, you're taking the derivatives individually, okay? Because differentiation and integration, indefinite integration, they're all linear operators. They're all linear, so if they respect addition and scalar multiplication. So here, L of f of x plus g of x, okay, is going to equal to, you're just taking the derivative of f of x plus g of x, which is, you just take the derivatives of them individually, which is f prime of x plus g prime of x. Oh, okay. What does this mean? This is equal to L of f of x plus g of f of x. So yeah, L is essentially, you can think of it as a derivative operator, because you're just differentiating f of x to get f prime of x, and oops, this should be g. Oh, what am I doing? This should be L of g of x. Okay, L of g of x is g prime of x. Okay, you can think of it as like a derivative operator for this particular example. It won't be the case for everything, but here we're just taking a function and we're sending it to its derivative. Okay, so now we're here more specifically a polynomial. Applying L to a polynomial sends it to its derivative. Okay, so we get that L respects addition. So now let's check for scalar multiplication, and because I said earlier that derivatives they respect scalar multiplication and addition, so yeah, L should respect scalar multiplication as well, but let's just show that. So f of x is in W and C is a real number, arbitrary. So L of C times f of x, this is equal to, you're just taking the derivative of C times f of x. Well, C is a constant, so you just have C multiply the derivative of f of x, which is f prime of x. Okay, the constant gets multiplied and afterwards. Okay, now f prime of x is L of f of x. So we get that L respects scalar multiplication. Okay, so therefore L is a linear transformation. And I guess I should have mentioned earlier in checking whether or not W is a subspace or not, I need to check if W is empty or not. Meaning, in order for it to be a subspace, I need at least one element. So that's just one nuance criteria. So, well, let's just see. Just say 0, right? 0 is in, we know 0 is in W, right? If I say f of x is the 0 polynomial, right? Then f of 0 is equal to 0. F of anything is equal to 0. So here we get W is non-empty. Okay. So right over here, another nuance criteria is that I need to show that L, well, because if I and II are true here for linear, for if L is a linear transformation, then I should get that L of 0 should equal to 0, which is true because if f of x is equal to 0, then f prime of x, the derivative of 0 is also equal to 0. The derivative of any constant is equal to 0. So that's true. Okay, so then this is actually just L of f of x, which goes to L of 0. Okay, so L of 0 is equal to 0. Okay, so that follows. Okay, so that's what we have over here. Okay, so now there's another way to actually show this part right over here. We don't have to necessarily take derivative because we know that if f of x is equal to 0 and L is linear, or it respects addition, then I have L of f of x, let's say minus f of x. This is just L of f of x minus L of f of x, which is equal to 0. And this is, the inside here is 0. So I have L of 0 is equal to 0. Okay, so that's that. It's all consistent, anywho. Okay. So yeah, that's what we have. It's pretty interesting. Okay. So I did make a video of this. I talked about this in the previous video. Okay. Now, this is all easy stuff, right? To show if something is a subspace or show that something is a linear transformation. Okay, you just use some algebra, and then you get it. Okay. Now, the harder part is 3. L is invertible, meaning, what does this mean? It means that L is both injective and, or I use a logical operator, and surjective. 1-to-1, both 1-to-1 and onto. Okay, so that's a question we should ask ourselves. Okay, so let's check L being injective. Okay, so remember the definition for injectivity. Okay, so L is injective if and only if the kernel of L is just equal to the zero polynomial. Okay, I talked about this in the previous video. So let's check. So let's show this. Okay, so let f of x be in the kernel of L. Okay, now the kernel of L is all the polynomials in W that whose derivative is equal to 0. Okay, so this implies that L of f of x is equal to 0. This is by definition, right? If f of x is in the kernel of L, then L of f of x is equal to 0. Okay, but L of f of x we said was equal to f prime of x, because that's what how it's defined. This transformation is defined. It sends a function, a polynomial, to its derivative. Okay, but because f of x is in the kernel of L, that derivative is equal to 0. So what does this mean? This implies we need to show that f of x is equal to 0. Okay, it's strictly equal to, it's identical to 0. Okay, so if the derivative of f of x, f prime of x, right? If that is equal to 0, what can we say about f of x? Derivative of what? What kind of functions do you take derivatives of to give you just 0? And by the way, f of x is a polynomial, so that should be easier. But in anywho, right? What kind of function's derivative gives you 0? It's a constant. So f of x is equal to a constant. Okay, it's a constant polynomial. It's a polynomial with degree 0. Okay, x to 0 we say by convention is 1 before you plug in anything into x. Okay, so we have f of x is equal to c. Now here's the thing though. F of x is in the kernel of L, okay? But we know f of x is also in W. What do we know about f of 0? Okay, kernel of L is a little subspace in W, okay? The kernel of L is a subspace of the domain, of our domain subspace W, okay? So now f of 0 is equal to 0, but f of x is equal to c. It doesn't matter what input you give me, my output is always equal to c. So 0 is equal to c here, okay? So which implies that f of x is equal to 0, because it's equal to c. And that c is equal to 0, because f of 0 is equal to 0. And in fact, f of x is equal to that 0 for all x. So we get f of x is equal to 0. So then we can say that I chose an arbitrary function, or arbitrary polynomial in the kernel of L, and I can conclude that f of x is equal to 0. So that's the only thing in the kernel. Only 0 is in the kernel of L. And besides, that is true for, that's true all the time, right? Like the 0 is always in the kernel of L, right? But we're trying to see is it the only thing in the kernel of L? If there are other elements besides 0 in the kernel of L, then L is not injective. But here we show that if f of x is in the kernel of L, then f of x has to just be 0. Just the 0 polynomial, just 0, okay? So we get that the kernel of L is just equal to the 0 polynomial, okay? 0. is just equal to 0. Okay, the set of just this one element, 0, which implies L is indeed injective. Okay, now let's check for surjectivity. We're on to. So this one is I would say it's a bit harder. So I would say L is surjective L is surjective if and only if for every what? For every g of x, because remember, we're going from we're going from w to v, where v is polynomials with real coefficients. Okay, so if and only if, I would say the range of L, or sometimes people will say the image of L is equal to V. Okay? Or, in other words, for every g of x, for every polynomial with real coefficients g of x in V, there will exist an f of x in W. So f of x is a polynomial with real coefficients, with the exception that f of 0 is equal to 0. I should say with an add-on, right? So f of 0 is equal to 0. So there exists f of x in W. Okay. So give me any for every g of x in V. Does there, if it exists, if it is the case that there exists f of x in W such that L of f of x, which equals to f prime of x, is equal to g of x. So if you give me any g of x in V, if that is the case, and there exists f of x in W such that the derivative of f is equal to g, then L is surjective. Okay, so how do we do that? So let g of x, you start with the codomain. Okay, so g of x be in V, which I said was polynomials with real coefficients, right? And this is equal to a n to the xn plus ... plus a0, okay, where n is just where all the ai's are real numbers, right, for I between 0 and n. Okay, so here we have a polynomial with real coefficients. The ai's are just the coefficients, a0 all the way to an. So if this is the case, then, and let's just say, is it possible for me to find an f of x so that the derivative f prime of x is equal to g of x? Okay, so suppose I found it. So suppose I found one. Okay, f of x. Is this the case? So we're kind of working backwards here. Okay, we're setting this. Let's try it out. So try to set. So set this equal to f prime of x, right? Where f of x is in W. Okay. F prime of x is equal to L of f of x, where f of x is in W, which obviously implies that f of 0 is equal to 0. okay, by definition. That's how you have f of x to be in W, f of 0 has to be in, f of 0 has to equal 0. Okay, so we're trying to set g of x to be equal to f prime of x. Then what does this mean? It means that the integral of g of x dx should equal to f of x, right? Now, the way we do it, we do this here was kind of interesting, because I guess we kind of already assumed that there does exist a f of x, so that f prime of x is equal to g of x, but we don't know, right? So here we're just assuming we can. So now let's just take the integral of g of x dx. So the integral of g of x dx is just going to be equal to an x to the n plus 1 over n plus 1 plus dot 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 plus a naught or a0 times x plus the constant c. Okay, we have a constant of integration. Okay, so now I'll call this part capital G of x plus c, where capital G of x has no constants. It's just a polynomial with no constants. What does this mean? It means that what happens if I call this, let's say, if I call this f of x, right? Because earlier we set this equal to f prime of x. That means the integral of this should give me f of x, okay? But we have a constant of integration, c. Okay, so now we have f of 0 is equal to g of 0 plus c. Okay, what is f of 0 equal to? F of 0 is equal to 0, right? So f of 0 is equal to 0. And what's g of 0? Well, this g of x is a polynomial with no constants. So g of 0 is also equal to 0 plus c. So g of 0 is equal to 0, and then we have plus c, which is equal to c. So 0 is equal to c. So this implies that f of x is equal to g of x plus 0, right, which is just capital G of x. So we can define f of x to just be equal to the indefinite integral of g of x with where the constant of integration is 0, right? So there we have it. You give me any g of x, you give me any arbitrary g of x, polynomial with real coefficients, and I will choose my f of x to be equal to the indefinite integral of g of x with a constant of integration equal to 0. Okay, so there I have it. I found it. So yes, there does exist a polynomial, right? A polynomial, capital G of x. I set that equal to little f of x. Okay, this is going to be a polynomial with real coefficients, right? And then f of 0 is equal to g of 0, which equals to 0. Okay, indeed, this is true, because g of x is a polynomial with no constant. It's just x's. Okay, when you plug in 0 into the x, you just get 0 plus 0 plus 0 plus 0, which equals to 0. So all you have is 0. Okay, so this part to show surjectivity is a bit more difficult, I would say, because here we're essentially just working backwards, trying to see if I can find a polynomial in my domain so that its derivative is my g of x in my little g of x in my codomain. Okay, so essentially just working backwards. Okay, and of course, in order for me to work backwards, I must make sure that my final f of x that I found indeed satisfies the fact that f of 0 is equal to 0, which is good, right? I could do that. Okay, so essentially, you give me any g of x in my codomain, I will find you an f of x in my domain where f of x is just equal to this. Okay, because this is in W, right? This is a polynomial with real coefficients, okay, such that when I plug in 0 into x, I get 0. If I differentiate this, then I will get precisely this over here. So that is good. Okay, because we said that the constant of integration was equal to 0. What a long question, but hopefully this makes sense. Do review surjectivity more. I'm still trying to figure out a better way to explain how to show surjectivity, but essentially it is given any output, right, or given any element in the codomain, can I find an element in the domain that maps to it, right? This is very similar to epsilon-delta proofs. Okay, for epsilon-delta, for limits, you also work backwards as well. Okay, so we're trying to see, does there exist a delta for every epsilon? But once you do find that delta, then you say, oh, it satisfies so-and-so condition, and therefore the limit converges, or or the limit exists or something, or converges to some value. So here, also working backwards. Give me any arbitrary element in the codomain. Can I find an element in the domain that maps to it?